Hello, and welcome to our presentation. When brainstorming for this project, we asked, how much power does a computer really use in a day? What about a TV set and everything attached to it? How much power does a living room use when not in use? Power meters show the whole power usage of a house, but what about specific devices inside? We are group number 7. My name is Nathan Locko, and I'm joined by my 4 teammates Martin Anderson, Jasmine Ford, Darian Langler, and Jackie O. This is our 499 project, the Modular Smart Power Bar.
This project's main motivation is to reduce the effects of vampire power. Vampire power is essentially the power that is lost from an electric device when it's left idly plugged into a wall. As you can see from the graph here, vampire power can account for approximately 10% of all power drawn by the device. The easiest way to eliminate the effects of vampire power is to have the electric device actually switched off from the wall when it's not in use. Our team decided that the best way to do this would be with a smart power bar. Jasmine will now talk about the goals we laid out at the start of this project.
The main goals of this project were to design a prototype for a user-friendly smart power bar for residential usage, with features including power data measured from each connected load, up to 6 modular outlets that can be a combination of 120-volt mains and 5-volt USB types, which can be connected as needed and programmed wirelessly for enhanced customizability. We hope to target the environmentally conscious consumer who is interested in educating themselves on their residential power usage and providing a useful and convenient solution to reduce unnecessary power loss that will subsequently help lower household electrical bills.
Thank you, Jasmine, for presenting our project goals. We'll move on to our design methodology, starting with the power system. On the right here, you will see our schematic for the power system. We're given a 120-volt AC source as our input, provided from a wall outlet. And the circuit needs to provide that same voltage as well as a 5-volt and 3.3-volt DC output. The 120-volt source is for any product that will be plugged in normally. The 5-volt source powers the microcontroller and also powers the USB ports. The 3.3-volt source powers the control circuitry and is also needed by the microcontroller. The 5-volt and 3.3-volt sources are made by using a transformer to get the right voltage values before passing that signal through a bridge rectifier, which is used to create a DC voltage from the AC source. The fuse and switch on the diagram are placed into the schematic as a manual on-off switch, and the fuse as our surge protection from the wall outlet. I'll pass the presentation back over to Jasmine to present our control system.
The main idea behind the control system design is to provide circuitry for measuring the current and power drawn by each connected load, as well as to develop a means of controlling the output of each outlet module. This system is closely connected with the microcontroller subsystem, which will be the source of signals being sent to control the state of each module, as well as the destination for storing power data measured by the current sensors. This will all be done via the I2C communication protocol. The implemented current sensing circuitry uses a differential Hall effect sensor to measure the current and calculate the power being dissipated for a particular outlet, and will also be able to detect when a module is in standby mode. For the 120-volt mains outlets, a triac-driven opto-isolator has been designed to control the state of a given module based on the control signal from the microcontroller, and for the USB modules, this is done using a current-limited power distribution switch.
To make this system truly smart, some kind of wireless user control was needed. To meet the goal of tracking power and controlling the modules, a microcontroller-based solution was theorized to be effective. The system should utilize Wi-Fi and a wired communication protocol in order to control and evaluate each module while storing power data. Factors considered when designing a microcontroller system was the available communication methods and their speeds, required complexity of this design, storage volume, and the price. After objectively comparing multiple devices, the Adafruit Feather with internal Wi-Fi module, as seen on the left here, was chosen. The full system derived utilizes an external microSD card via the SPI protocol and uses an I2C bus to communicate with the modules. I2C was chosen here due to its common bidirectional bus communication method and its prevalence in industry and components. SPI, meanwhile, keeps the data management separate from the busy I2C bus, and mini SD cards can already function in this protocol already. The final design can be seen here on the right. Through calculations and testing performed, it was shown that this solution is simple, cheap, and effective at meeting this project's goals and objectives.
For this project, 3 PCBs were designed individually for each of the respective modules. This was primarily done because each of the modules has very different needs, electrically speaking. For example, the USB module doesn't need any high voltage power switching, and the high voltage module doesn't need a 5-volt power supply. Our team opted to keep the PCB 2 layers thick, just to ensure that the overall cost of the device is not higher than it needs to be. It was also important during the PCB design process to keep the I2C lines on each of the modules as far away from the noisy high voltage sections of the board, just to reduce the chance that there was any interference.
The design of the enclosure was completed using an iterative process. The features for the enclosure were decided upon as the other subsystems were being developed and finished, as the enclosure needed to enable and showcase the functionality of said systems. 2 modules were designed to meet the modularity objective: NEMA 5 plug and USB outlet. These modules can be added on and rearranged to whatever the order desired by the end user, giving the system a lot of flexibility. At the end is a removable terminal, which not only closes the I2C circuitry, but also protects the outside environment from the 120-volt hot rails.
Since this device is intended to be enlightening and user-driven, an informative and convenient user interface in the form of an app is desired. UIs are very much artistic endeavors done close to the end of production. As such, only the basic frame and necessary features such as the home screen were designed. From the app, the user would be able to view power data, turn on and off devices, change settings, and troubleshoot errors. Displayed on the left is the data screen. This is where users can view and track their power usage for their computers and other electronics over time. The graph can be zoomed in and out to see specific date ranges, with averages and totals also displayed. From the settings screen, users can take control of their power usage with intelligent settings and save on power waste.
These are all of our systems. I will now discuss the results that we have obtained from them. As the UI has an artistic and subjective nature, we have designed a placeholder which includes our intended features. However, we would look to improve it with future work. The microcontroller system is based off the Adafruit Feather Huzzah, which communicates with its ESP8266 Wi-Fi module. It has the benefit of working efficiently while still coming in at a low cost of $17. The controller will communicate via the I2C protocol and uses an SPI SD card to hold upwards of 3 years of power data. The power system was able to create the necessary voltage. However, the design produces low currents on the 5-volt and 3.3-volt lines and will need to be improved further with future work. The control circuitry was able to get positive results from simulation testing, but it also experienced some current issues and will need to be improved with future work. The PCB design works with all other systems and allows them to reach the requirements necessary. It could be further improved with future work, but fulfills all the goals we had set for the system. I will pass it off to Jack now for our conclusion.
In conclusion, the final design solution sufficiently meets the listed design objectives. We created a design to address the problem of phantom load from devices that are continuously consuming power in standby mode. We're able to target environmentally aware consumers who are interested in reducing their energy footprint. The power bar utilizes a microcontroller with the capability for a user interface to better the consumer's experience with the product and provide improved feedback and understanding on residential energy use. To achieve a better share of the market, a modular system was adopted to provide the flexibility to match the user's needs. Though a physical prototype was not feasible for this endeavor, the performed tests and simulations provide the confidence and validation that the presented solution will be successful, with some future work to improve upon current issues.
Due to constraints mentioned previously, the team was not able to fully prototype and test this design. As such, some recommendations of future work have been made. The first and most important would be to order the PCB and the parts to fully develop and test the prototype's electronics. From here, a fuller UI should be developed and tested with the device as well. The enclosure design should also be formed and tested for connectability and robustness, preferably with the use of a 3D printer for rapid development. From here, the simulated design should be fully tested through this physical system, and any shortcomings should be iterated upon and improved. Once fully tested and working, other features that were intended to be developed, such as the 2D modularity, can be designed and tested further to form a full product.
And thank you for watching. From Group 7, I hope you enjoyed our presentation.